If someone tells you humans have made transistors down to the size of a few atoms, would you believe it? And here's the incredible thing. As electrons flow through these tiny transistors, they start to fade away. Mysterious appearance on the other side. It completely violates the principles of classical physics. This is not science fiction. It is a real crisis at the forefront of today's semiconductor industry. Think about that. As transistors continue to shrink, and it ends up being as thin as an atom, where will the electrons flow through? It sounds like a physics paradox, but in the semiconductor industry, this impossible wall is rapidly approaching. TSMC has announced the upcoming mass production of the 2nm process node. Samsung and Intel followed suit. However, when the ridge was only a few atoms thick, quantum tunneling takes hold. Electrons pass through the wall like ghosts, causes a large leakage current and power consumption explosion. Is the golden age of silicon-based chips really coming to an end? We all know that. Moore's law, which doubles the number of transistors every 18 to 24 months, has ruled the semiconductor industry for more than half a century. It was 1965. Intel co-founder Gordon Moore observed the development of early integrated circuits. This famous prediction was made. At first, he thought transistor density was doubling every year. It was later revised to double every 2 years. But less well known is, this is not a law of nature at all. It is a technological roadmap that the entire industry shares. Under the guidance of this roadmap, chip fabrication has shrunk rapidly from 10 microns in 1971 to 3 nanometers in mass production today, shrunk by a staggering 333 times. It is this exponential progress. We have smartphones in our pockets that are millions of times more powerful than the supercomputers of the 1970s. However, the natural world, the physical barriers set up are approaching us. The gate thickness of transistors in today's 3nm process is approaching the thickness of stacks of 5 to 7 silicon atoms. The upcoming 2nm node will further compress this size. This brings up the fatal problem of quantum tunneling. Think about that. Think about that. If I told you that a ping pong ball can magically pass through a wall without any kinetic energy, you will surely scoff. But at the quantum scale, electrons can indeed do this. When the thickness of the tertiary oxide layer approaches 1 nanometer, electrons that were supposed to be blocked begin to pass through the wall through quantum tunneling. This results in current leakage and power consumption spikes. In 2023, TSMC's research published in Semiconductor Science shows that, in the 2nm node test chip, the mountain-scale leakage current increased by nearly 300% compared to the 5nm node. This means that chips with the same performance may need to consume more power, generate more heat. In addition to the tunneling effect, another lesser-known enemy is quietly disrupting the charge capture of ultra-miniature transistors. There are a large number of atomic-scale defects in the ultra-thin oxide layer. These defects trap passing electrons, just as potholes on the road can jam a wheel. Over time, these trapped charges cause transistor characteristics to drift, make the chip run slower. Ultimately, it could lead to the collapse of the entire system. The latest data shows that, in test samples at the 2nm node, the amount of charge or resulting device aging is 2.5 times faster than the 5nm node. This means that the chip lifespan may be significantly shortened under the same conditions. This is one of the reasons why even flagship phones only offer 2 to 3 years of system update support in recent years. Hardware itself is facing atomic aging. You might ask, why can't scientists continue to shrink transistor sizes? The answer lies in the limitations of lithography. Lithography is like drawing a circuit diagram on a silicon chip with a light pen. For a long time, the shortening of the lithography wavelength has been a key to advancing the process. The current state-of-the-art extreme, ultraviolet lithography technology uses a light source with a wavelength of 13.5 nanometers. But that's not enough to imagine the difficulty of drawing fine patterns with a thick pen. Even the most professional painter cannot draw hair-like lines with a brush the thickness of his thumb. Lithography also faces a similar dilemma. When the pattern to be depicted is about 2 nanometers, it is much smaller than the wavelength of light 13.5 nanometers. The diffraction effect makes accurate imaging nearly impossible. The Dutch company ASML is developing the next generation of high numerical aperture UV lithography machines. Raise the numerical aperture of the optical system from 0.33 to 0.55. Theoretically, the resolution can be advanced from 36 nanometers to about 30 nanometers, but the device is expected to cost more than $400 million. That's more than twice the size of current EUV devices. And the first batch of machines won't be put into use until the end of 2025 at the facing the silicon plane scaled ceiling. The semiconductor industry is actively exploring multiple technological paths. Sometimes the best strategy is to make peace with the enemy. Since quantum tunneling cannot be avoided, So the scientists decided to take advantage of it. Tunneling field effect transistor is a new device based on the principle of electron tunneling. Compared to traditional MOS, TFETs enable steeper switching characteristics at low voltage. It means that the current can be switched on and off with a lower voltage. This results in a significant reduction in power consumption. An experimental TFET, developed by Intel and Tsinghua University in Taiwan, demonstrated 70% lower power consumption than a FinFET of the same size in 2023, while maintaining considerable performance. If silicon has reached its limit, why not change the material? Carbon nanotube field effect transistors demonstrate amazing properties in a laboratory setting. The carrier mobility is 10 times higher than that of silicon. This means that electrons can pass through transistors much faster. In addition, its ultra-thin structure is 1 to 2 nanometers in diameter. It performs well in resisting short channel effects. In early 2024, the Stanford team reports the first Dow carbon nanotube integrated circuit in Nature Electronics. It has over 10,000 transistors, capable of performing simple computational tasks, although it is still far from commercial use. But this breakthrough proves that carbon-based electronics is no longer science fiction. The other star material is a two-dimensional transition metal dies, such as molybdenum. These materials are only 3 atomic layers thick, about 0.65 nanometers. However, it can exhibit excellent semiconductor characteristics. Research from MIT shows that the MOS2 transistor can still maintain a good switching ratio at a nanometer gate length. However, silicon transistors of the same size have long since failed completely. If there is no path on the plane, why not move up? Just as skyscrapers provide more space on limited urban land, 3D stacking technology allows the chip to expand vertically. This strategy has achieved tremendous success in the storage sector. Samsung's 3D NAND has stacked over 200 layers of storage cells. The plain NAND has long been unable to continue to shrink. In the field of logic chips, by splitting a large chip into multiple smaller chips, and then through advanced packaging technology. For example, Intel's EMIB TSMC's INFO or Samsung's IQ are connected together, achieve higher integration and lower manufacturing costs. AMD's Ryzen processor uses this technology. Separate the CPU core and I/O modules. Not only increases the yield, it also achieves a perfect balance between high performance and low power consumption. The flagship Rulon 9 processor in 2024, 12 CPUs made using TSMC's 4 nanometers process. 25% better performance than the previous generation, the power consumption has dropped by 15%. As we approach the limit of Moore's law, the world's 3 largest wafer manufacturing giants are competing fiercely. TSMC will take the lead in mass-producing a 3-nanometer process in 2022, and an optimized version of N3E will be launched in 2023. According to data released by TSMC, the N3 process offers a 10 to 15% performance improvement over 5 nanometers, or 25 to 30% reduction in power consumption. Apple's A17 Pro and M3 chipsets are both manufactured using this process. And here's the thing, TSMC's 2-nanometer node is expected to be completed in the 4th year of 2025. Quarterly production, N2 uses a groundbreaking surround gate nanosheet transistor architecture. 10 to 15% performance improvement, or 25 to 30% reduction in power consumption. According to Barron's, TSMC CEO Wei Zhepia predicted more than $2 trillion worth of products will use its 2-nanometer technology in the next 5 years. Samsung preemptively launched the world's first commercial 3-gate full surround process in 2022, self-proclaimed multi-bridge channel FED. According to data released by Samsung News Center, compared to the 5-nanometer FinFET process, the 3GAA achieved a performance improvement of about 23%, 45% power reduction, and 16% area reduction. However, according to The Verge, Samsung's 3-nanometer yield was only about 20% in the early stage, far less than 85% of its 5-nanometer process. This has also led to the addition of Samsung's own Exynos processors. Few high-end customers choose this process. As a former process leader, Intel has run into technical bottlenecks in recent years. In the first half of 2024, Intel has finally started mass production of the Intel 3 process equivalent to the industry's 3-nanometer level. According to Patent PC's analysis, Intel 3 uses nanoribbon GA technology. The target is a high-performance application scenario of 1.2 volts. Intel CEO Pat Kissinger once confidently declared, by 2025, Intel will return to its process leadership position. However, considering the rapid progress of TSMC and Samsung, whether this goal can be achieved remains highly uncertain. When the silicon plane scaling approaches the limit, what is the future of computing? Experts agree that the next decade could be an era of diverse innovation. In the short term, 3 to 5 years, GAA architecture, HIN AEUV, and heterogeneous integration will continue to drive performance improvements on traditional chips. Midterm, 5 to 10 years. New materials such as IVE semiconductors and carbon nanotubes may gradually enter the mainstream. In the long run, more than 10 years, new computing paradigms such as TOPU quantum computing and spintronics could lead to revolutionary breakthroughs. As Intel founder Gordon Moore said in a 2015 interview with nothing never ends. But nothing ended abruptly either. Moore's law may be slowing down, but humanity's quest for greater computing power never stops. Do you think that as silicon-based chips approach their physical limits, which alternative technology is most likely to lead the next computing revolution? Carbon nanotubes, quantum computing, or is it some kind of entirely new computing paradigm? Share your thoughts in the comment section. As physicist Richard Feynman said, there's infinite space at the bottom, even at the atomic scale. The boundaries of science may still have to be explored and broken through.